Okay, Algebra 2, mindful percent manipulations. So, percents and phenomena that grow at a constant percent rate can be challenging to say the least. This is due to the fact that unlike linear phenomena, the growth rate indicates a constant multiplier effect instead of a constant additive effect, as in the case of linear functions. And because constant percent growth is so common in everyday life, not to mention science, business, other fields, it's good to be able to mindfully manipulate those percents. So we got an example here about a population of wombats growing at a constant percent rate. If the population on January 1st is 1027 and a year later it's 1079, what is the yearly percent growth rate? Percent? Okay, this is an old formula where you subtract the old from the new and then divide by the old and then multiply by 100 and you've got the percent increase. It's really just percent change. It just happens to be increasing, so they're calling it percent increase. So in this case, a percent increase would be 1079 minus 1027. Those absolute value bars are to just ignore the sign in the event that the new is smaller than the old, but in that case, it would be a percent decrease. That's a little strange. Think about it. Yeah, have to think about that. Anyways, I'm getting about a 5.1% increase. And so that's that. Now let's try to determine what the percent growth in wombat population will be over a decade. So first they want us to write an exponential model, calling it W of t, where we have our initial amount times our percent growth rate added on to 100 to the t power. So 100% plus 5.1% is 105.1% converted to decimal form there. And then after 10 years, what will we have multiplied the original population by? So this is not evaluate the function at 10 years. It's literally just saying, okay, what is the 1027 getting multiplied by? So it's actually just a little bit easier than that. That it's 1.64, and then it says using your answer from part B, what's the decade percent growth rate? In other words, what they're getting at is we could do this. We could do and get 1,688.88 wombats in 10 years. And then do the percent growth calculation. And we get about 64.4%, right? But what they're saying is, hey, look, this is 164%. We could have just subtracted 100 and said, oh, it grew by 64%. This is just a great way to check. All right, sticking with the wombats. Assuming their growth rate is constant over time, what is their monthly growth rate? Okay, well, this is a yearly growth rate. How many months in a year? 12. But here's the deal. Percents grow by multiplying over time. They grow exponentially, right? So since we're using exponents, we have to think what operation reverses exponents? Well, just as everything has an opposite in terms of operations, addition and subtraction, multiplication and division, squares and square roots. Well, powers in general, like raising something to the 12th power, the inverse is the root. So this would be the 12th root. And a little review, this would be helpful if you're using a scientific calculator as well, that's equivalent to raising 1.05 to the 1/12th power. And I'm getting that this is about 1.00415, which remember is in decimal form because this is originally in decimal form. So that is equivalent to 100.415%. So our growth rate is 0.415%. Remember, these are percents. Let me revise that a little because they did say to the nearest tenth of a percent. Okay, moving on. All right, now we got a new population growing at a rate of 22% every 5 years. Okay, so keep in mind that that's a growing, so it's 100% plus 22%. So our multiplier is 122%. In decimal form, that's 1.22. Now that's every 5 years. So if we want to know how much every year, we'll keep in mind that it's been multiplied by something smaller every year for 5 years to get to 22% over the 5 year period. So if we want to get at smaller value, that yearly value, we need to take the fifth root. I'm going to make that a little neater. And this is approximately, a little reminder, this is exactly equivalent to 1.22 to the 1/5 power. And so I'm getting about 1.04. And this is a signal, this is an expression that'll calculate the single year percent growth rate. And then, so here's my expression. And then here it is. So our yearly percent growth rate would still be 104 minus 100 is 4% yearly. Okay. All right. Over a 2 year time span. Okay, so we're going to take some unknown amount and multiply it by 1.04. That would be the amount after year one. Then we multiply that amount again by 1.04, and that would be the amount after year two. Or alternatively, we could just take this unknown population, we could multiply it by 1.04 to the second power. It's just a little more efficient, does the same job. Here I'm getting approximately 1.0816. Let's see. So then remember that is 108.16%. I'm subtracting 100. And I'm getting 8 to the nearest tenth, 8.2% growth over that 2 year time span. Okay, 43, world oil reserves. The amount of unused oil in the ground are depleting at a constant 2% per year. We'd like to determine what the percent decline will be over the next 20 years based on this 2% yearly decline. So this, again, now we're finally dealing with percent decrease. So we have to consider the fact that, okay, we start with 100%, we lose 2% a year. So we have 98% of what we had the previous year. In decimal form, that's 0.98. And this is happening year after year after year. So 98% of what we had, then 98% of what we had, then 98% of what we had. And it's decreasing. It's decreasing by a little less each year because there is a little less of it. So we have 0.98 times 0.98 times 0.98 times 0.98, 20 times, which is approximately 0.67, which is equivalent to about 67%. Write the expression, did it, that's there, and then calculate it to the nearest 100th, so that would be here. Let's see, use your answer, A, to determine the percent decline after 20 years. Okay, so that's not the percent decline, that's the amount that we have. We have 67% of the oil that we had 20 years ago now. So let's subtract 67% from 100 and get 33% decline in oil or decrease. This is a little crazier than just like, okay, get an answer and move on. This is something that's worth taking the time to think about. This means that a third of the oil in the world will be gone in 20 years. This is something we need to be very aware of as we, consider how much we use our cars, buy gas. and it's why we're looking into electric cars and other alternatives such as solar power, wind power. Okay, turn to the page. Here's one where, okay, we're talking about revenue for a restaurant. It's increasing by 5.25% over the previous year. So right off the bat, we got 105.25% in decimal form, 1.0525. But that is yearly. If we want monthly, we're going to have to calculate the 12th root. There's not a ton of room here, so I'm going to just immediately convert it to the fraction form to review, getting approximately 1.00427, which narrows it down to these two. But this is new. We have a multiplier in the exponent. So what I like to think about here is that these need to balance each other out. We just took the 12th root, so to balance it out, we need to multiply by 12. But if you want to know like a common sense reason, it's because this rate here is monthly, but the calculations are still in years. So if I'm inputting a monthly amount here, I need to uh, multiply 12t. 12t time is still in years here. So 12t equals number of months we're dealing with. Half-life. Half-life is the amount of time needed for 50% of the substance to decay. 50% is 0.5 in decimal form, so you could put 0.5 there in that formula and be just as accurate. Don't be thrown off by these. Q stands for quantity here, just how much is there, and Q0, or often called Q naught, which is spelled like that, is just Q, the quantity at the beginning, quantity when time is 0. Okay. So what are we dealing with here? Cobalt. Cobalt has a half-life of 5.2714 years. Here's the formula. That's how you bring in the half-life. You just throw it in, dividing the T by that half-life. So what do we want? What is it decreasing? The amount is decreasing by approximately what rate each year? So this is pretty wild, but here's what you're going to do. You're going to take 1/2 to the T over 5.2714. Using our exponent properties, we can convert that to so to calculate this, I'm going to just go to Desmos, guys, because that's an insane root, right? And get 0.8767 roughly, right? So back, and now I finally have a single rate, and I can say, okay, so we have 88% of what we originally had, right? Well, that means that it's decreasing by 12% a year. Okay, and then lastly, here's my function running low on time, so I'm just going to get you this one as quickly as possible. All right, I got to input the half-life, which is 20 years, and then here we just have to input 40. Well, 40 over 20 can be reduced there in the exponent, so that's 2. And 0.5 is 1/2. 1/2 squared is 1/4. So we got 50. 1/4 of 100 is 25, so 1/4 of 50, 200 is 50 grams. And I'm about out of time. But that'll do it. And miss you guys. Hope all is well. Keep in touch.